Welcome. So this session introduced the concept of differentiability of a function of complex variables. So we start by defining what we mean by differentiability of a function of complex variable, and then do some examples. So let f of z be a single valued function of the complex variable z, then a derivative of f of z is another function f prime of z given by f prime of z equals to limit as small change in z approaches 0 of f of z plus small change in z minus f of z divided by small change in z, provided that the limit exists and is independent of the path along which the small change in z is approaching 0. So that's how we define a derivative of function of complex variable. Some methods of differentiation. So one first principle, as we saw in the case of function of real valued for functions of real numbers, product rule, chain rule, quotient rule, all those applies as we saw for the case of function of real numbers. So examples. Use first principle to evaluate the derivatives of the following. So A, W equals to f of z given by z squared. Now, solution. So first principle is simply the definition. So the W dz, which is the same as the F dz, or the F prime of z, is limit as small change in z approaches 0, F of z plus small change in z minus F of z divided by small change in z. So here, F of z is z squared. This is already given. And then F of z plus delta z is given by delta z plus delta z squared, which is z into z plus delta z into z plus delta z. So this will be z squared plus z delta z plus z delta z plus delta z squared. Now, using these values in the definition, this means df dz, which is the f prime of z, is z squared plus, this will be 2 z delta z plus delta z square minus f of z is z squared divided by delta z. So that means that minus z squared plus z squared, which will give us f prime of z equals to, we can actually factor out delta z and say 2z plus delta z. Okay, there's a limit as delta z approaches 0 of this quantity. So this will be limit as delta z approaches 0. Now delta z is common, so 2z plus delta z over delta z. So delta z cancels out, and we'll have f prime of z equals to limit as delta z approaches 0, 2z plus delta z. And it's not hard to see that this will be 2z plus 0, which is just 2z. So that's the derivative. Number 2, w equals to f of z equals to 3z squared minus 2z plus 5. So as usual, you start from definition that the derivative f prime of z is the same as limit this by definition. So f of z is given by 3z squared minus 2z plus 5. This is already given. And then f of z plus delta z will be 3z plus delta z squared minus 2z plus delta z plus 5, which is 3 into z squared plus 2z delta z plus delta z squared minus 2z minus 2 delta z plus 5, which on simplification will give us 3z squared plus 6z delta z plus 3 delta z squared minus 2z minus 2 delta z plus 5. So thus f prime of z will be limit as delta z approaches 0 of now 3z squared plus 6z delta z plus 3 delta z squared minus 2z minus 2 delta z plus 5. And then we subtract this. So every term here, the sign will change. Minus 3z squared. This being minus will be plus 2z. This being plus will be minus 5 over delta z. So that will give us this cancels with this, 2z minus 2z minus 5 plus 5. So this will be limit as delta z approaches 0. Now you see that the remaining terms delta z is common, so I can say delta z into this will have 6z plus 3 delta z and then minus 2 this part over delta z. So delta z cancels out. So this implies f prime of z equals to limit as delta z approaches 0 of 6z plus 3 delta z minus 2. Direct substitution now gives 6z plus 3 times 0 minus 2, and this simplifies to 6z minus 2. So that is how we get the solution. Actually, the process is just the same as what you do when you're dealing with real valued functions. Now, example 2, use power rule to evaluate the derivatives of the following. So 1, 6z squared plus 4z plus 8. So this is f of z. Now solution. So remember, power rule states that if f of z is given by z power n, then f prime of z is n z raised power n minus 1. Similarly, if f of z is a z power n, then f prime of z is given by n a z power n minus 1. In the same way we deal with real valued functions. So here, f prime of z, which is df dz, will be 2 times 6, which is 12, z plus 1 times 4, which is 4, and then 1 minus 1, 0, z power 0, 1. So this will be 4. Derivative of a constant is 0. So this will be the solution. B, f of z equals to 6x power 5, 6z power 5 plus 10z power 4 plus 6z power 3 plus 10z plus 99 plus 199. Similarly, there's the same way we deal with real valued functions. The derivative of this will be 30z power 4 plus 40z power 3 plus 3 times 6 is 18z squared plus 10. The derivative of a constant is 0. So this will be the solution. C, f of z equals to square root of z plus z power pi plus 16z power third. Say 163 z power third plus 10. So f of z in this case can be written as, remember, square root is the same as raised power half. So plus z power pi plus 163 z power third plus 10. So this means that the derivative is the same as a half z power minus a half plus pi z raised power pi minus 1 plus 163 times a third z raised power negative 2 over 3 as the solution. In a similar nature, the way we applied quotient rule, product rule, chain rule, for the case of single valued functions or real valued functions are exactly the same for this case. The only difference is that the variable that we'll be using will be z, but the way of application is the same. So next session will give more other information regarding differentiability of functions of a complex variable. Thank you.